Okay, so this is problem 3-2. This problem has a 20 kilogram block on a 30-degree frictionless slope. And then further down the slope is a spring with a constant of 200 newtons per meter. Part A in this question asks us to determine the speed of the block just before it hits the spring. This means we have to take the speed right at 6 meters of travel for the block. Without the spring, this problem is much easier. Being that the mechanical energy of this system is conserved, we are able to determine that the potential is equal to the kinetic energy. The potential for this block is mgl, and the kinetic is 1/2 mv squared. So, potential is mgl, and then the kinetic is 1/2 mv squared. Being that this block is on a slope, we take the vertical component of gravity for the distance it travels. This can be achieved by multiplying the distance it travels to the sine of the slope angle. So we have mgl sine theta for gravity equals 1/2 mv squared. And then substituting the values back into our equation, we get the mass is 20. So we get 20, we'll just use 10 for g. The length is 6, it travels 6 meters. And then the angle is 30. So plugging in values. And then sine of 30 is just half, so then the 6 goes to 3. So this side is just 30 equals half v squared. And then this is just 60 equals v squared. Square root both sides. We get v equals the square root of 60. Okay, part B. Part B asks us for how far the spring compresses when the block stops moving, meaning that when the kinetic energy of the block is equal to 0, then that is where we can find the distance that the spring compresses. When we release the block, the kinetic energy is 0, and then when the block is stopped at the bottom, the kinetic energy is also 0. So since the change in kinetic energy is 0, we can conclude that the change in potential energy must also be 0. So this means that the potential of the spring when the block is at rest is the same as the potential of the block due to gravity. From part A we saw that gravity was mgl sine 30, except that this time the block travels another 6 meters plus another x distance in the spring. So we can represent that distance as 6 plus x. So we have mg, the length is 6 plus x, sine 30, equal to the potential of the spring, which from our equation sheet we know is 1/2 kx squared. And then substituting values in, we have the mass is 20, gravity we can just use 10, we have 6 plus x, and then sine 30 we know is half. And this equals half, our k value is 200x squared. So now we can just do some canceling. This is just 200, so this cancels here and here. And so what we're left with is 6 plus x equals x squared. So just simplifying this a bit, we get x squared minus 6x, x squared minus x minus 6 equals 0. And then when we factor this down, we get x minus 3 and x plus 2. And this distance can only be positive, so we get our value as x equals 3 for the distance that the block compresses into the spring. Okay, part C. Part C asks if the speed of the block is at a maximum at the instant when the block hits a spring. At the instant that it hits a spring, the block is actually not traveling at its maximum velocity. So the answer is no. And this is because the mg component is still stronger than that of the spring component when it hits. The spring doesn't actually have any force built up when it just hits. So as the spring compresses, then the force of the spring increases. So to get to that point where it actually stops, to find where the block is at a maximum velocity, we find where the forces cancel each other out, because the block will just keep traveling faster and faster when the mg is bigger than that of the spring. And so it'll just keep traveling faster and faster, and they cancel themselves out. So the gravity component is mg sine theta, and then the spring component is kx. And then just plugging in values, so the block is 20, and then for simplicity we'll just use 10 for gravity. Sine theta we know is half, sine of 30, sorry. And then the k is given as 200, and then x is what we're solving for. So this is just 200 and then 100 equals 200x, and then x equals a half. So that's the distance into the spring at which the block is actually traveling at a maximum speed.